So where were we yesterday? We were talking about sorting very large data sets, so hundreds of thousands, millions, hundreds of millions, even maybe billions of items, and figuring out how we could deal with this when our computer's memory didn't necessarily have enough room in RAM. So our idea was to break things up into chunks and store those chunks on the hard drive, maybe even distribute them among a bunch of different computers. And then what we could do is we could sort each of the chunks independently and then merge them. Now, to do this, we needed to learn how to do file input and output operations in C, and that was where we ended off class yesterday. So we're going to start off today with a few different demos looking at ways that we can do file input and output to hopefully get you a little more familiar with the concepts before returning to a short discussion about merge sort, external merge sort, where we break things up into different files. And then we'll move on to our new topic, our last data structure, our second last data structure of the semester, because we're adding one this year. Our first program of today is twolines.c. It demonstrates much of what we've already seen. Yesterday we displayed how to write files, and today we're also going to display how to read them. This is a very simple example, so we'll go through it pretty quickly. Our main function here is interesting because it's going to, instead of taking in files using standard in like we did with that angle bracket symbol before, we're now going to take in the file name and process the file names that we get as arguments. So we're going to use argc and argv instead of our angle bracket. Now students often get pretty confused between these two different ways of reading in a file. So if you're using scanf, you're reading in whatever's coming in on standard in, this stream that we talked about yesterday. And so you don't need to do any of the file operations. However, seems to be plugged in poorly. However, if you want to read in, say, a larger number of files, you might take in those file names as arguments rather than feeding them all in on the input stream. This gives us some more flexibility around how we manage the files. So the first thing we're going to do is we're going to iterate through the number of from 1 to argc, where argc is going to be the number of files. But we're starting at 1 because remember, argc is going to give us the limit there. So we're going to print to standard error instead of to standard out because these are debug information. This is log information about the program. This is not actually the output of the operation we're trying to do. This is the program communicating to the developer or the person running the program how well the program is doing. So maybe it's about the progress of the program. Maybe it's had an error. Maybe it's been successful. These are the types of messages that would print to standard error rather than to standard out. Then same as we did yesterday, we're going to use one of our f functions, only this time we're calling fopen. And because we want to read in the file and figure out what are the first lines, we're going to use the access modifier of R here. And remember that these are strings, not characters. We talked about this yesterday. This would be the character version, which doesn't work. This is the string version, and we need it so that we can add the plus when we get to random access. If this doesn't work, so if this is equal to null, then our fopen function has not succeeded, and so we're going to print to standard error that it's failed. Otherwise, print the separator, which is going to be our just something to display to the user that we're now beginning a new file in the program so that they can see clearly in the output that this is part of a new file. So if we read 5 files, the first file, we'll see its output, then a line of equal signs, then the second file, then a line of equal signs. So it's just a visual separator. And then we run our first lines function with the file pointer and the line limit. So line limit is going to control how many lines from the file we read. In this case, it's just 2. So let's jump to first lines. We are going to do a standard getChar loop. And then we're going to print to the screen each character as we get it. Stopping if we get to EOF. And also noting that if we see a new line character, we're going to increment the number of lines we saw. So if we see 1 new line, the counter for lines is going to be 1. If we see 2 new lines, when we see the second one, it'll get to 2. We know we've seen 2, we have max 2, and so we're going to stop the loop. Then just print how many lines we've seen. So this one is fairly standard. And we're going to run this on, I've got a list of lots of people's names, and we're going to run it on the list of people's names. So here is shufflednames.txt. It's just a list of first names taken from the US Navy's database. And we're going to run it on this. So if we're running our program and we set lines to 2, we should expect to see the first 2 names, Justin and Odell. So let's see what happens. Oop. This was called 2lines.c. And let's run it on shuffled names. See Justin and Odell with all the debug output. Now if I run it with another text file, let's call this one just first names, it's another one. I will now see it opens the first file that I put in as an argument and then the second file. Now the reason they both have the same number of lines is because all shuffled names is it's a shuffled version of first names, and we'll see why we want this later when we go back to thinking about merge sort and how to sort large files with a lot of lines. Now, next program that we're going to look at, these we're just going to look at very briefly, are cat, tail, and WC. And all of these are built-in commands in Linux or in UNIX. Now, if I run cat on shuffled names, it's going to show me everything in that file. Cat is just a command that reads in a file and prints it out to the screen. What about tail? So I'm going to do tail, and I'll give it a -n argument of 2, and I will give it shuffled names. Give me the last 2 lines in the file. And finally, WC, which is our third utility, is going to give me the number of lines and the number of characters in the file. So these are 3 standard utilities. And now we're advanced enough, we've learned enough C that we can actually go look at the source code, at the actual code that makes these utilities work, and we could probably understand it. So I'm just going to show up on screen pretty quickly what each of these looks like. So cat, which was this program to just read in a file and print it out to the screen. So let's look at the structure of it. So the first thing it has is it's got this usage function. Now what is usage? Usage is what happens if I print cat-h or any program -h. It'll give us what is the way to use the program. Oh. So it told me that's an illegal option. -h obviously isn't a legitimate flag for cat, but it has printed its usage down below anyway. So a good thing for your program to do is if someone gives you the wrong arguments, to have it print its usage. Have it print a description of what the arguments should have been. Now this is not a complete man page, but it'll help just give you some guidelines. So that's this usage function, okay? We have a function to compute the line number we're up to, and then we have a simple cat, which, while true, read a block of input, check if we're not at end of file, and write out the block of output. Now the exact details of how cat works and how it ends up being a little more functional than our program that we just wrote are a bit much for the class, but with the links that I put online, feel free to go through it and look through, and you'll see that now you're at the point where you can actually understand most of these operations. So that's cat. Let's look at tail. And this one I just want to browse through and show you roughly how long the program is. This is a standard program that's used hundreds of thousands of times every day by developers all around the world. Let's look at how long it is. So they've got all these extra header files which have different library functions. It's got some authors in there just like we've been doing. And then let's just scroll through and see how long it is. So let's get to the bottom in a second. So that's 2,490 lines of code for something as simple as printing the last 2 lines of a file. Now you might ask, why so many lines? Why do we actually need all these things? Well, if we go to the man pages, let's do man tail, we can see that it's got all these different flags and all these different ways that it can be used. So we could read in from a certain number of bytes, we could read in a certain number of lines, we could read in a certain number of characters. And so even while the functionality is relatively simple, to make it work in a fashion that's portable, that'll work on any computer, that'll work with many different types of files, that will give it all these different options, that ends up expanding the code base. However, I would encourage you to go away and write these 3 different utilities, cat, tail, and WC on your own. Not the full 2,500 line version, but just a simple version, and that'll get you used to playing around with files. Okay, we've got one more demo in this lot, and this is our fread demo. So this one is kind of similar to what I was doing before on my live coding demo, except now we are going to do it with non-ASCII values. So instead of reading and writing characters, I'm going to show you how we can do this with integers as well. So just like before, I'm going to name a file pointer, declare an array that's going to be the elements that we'll read in and write out, and I'm going to initialize the array. And the way I'm going to initialize it is just, this is some arbitrary function. There's nothing meaningful here, so it doesn't really matter. We're just filling out some interesting data for us to read and write. We're going to print that to the screen just so we know what we're doing. Open the file. Remember, we have to do the check to make sure it succeeded. Write them just using the same syntax that we did yesterday. Clear the array. So now it's going to be set to 0. There's nothing in the array anymore. And now what I'm going to do is refill that array with what I just wrote to the file to show you how you can take stuff that's in your memory, push it out to a file, and then get it back from the file at a later date. So we need to make sure that our array is large enough to hold all the stuff that we're going to read in. And then we're going to call, let's ignore this for the minute and jump here. We're going to read the array back. It has almost identical syntax to our write over here. So this was source. The size of the elements that we're going to be writing, how many elements, and the destination. In this case, now that we're reading, FP is now the source, A is the destination, the size of the items that we want to read, and how many of them we're going to read in. And then we'll just print our array again. Now, this reopen function, why do I need the reopen function? Why couldn't I just reuse the file pointer that I had before? You've answered me plenty. Bruce, what do you think? Oh, sorry. Yeah, go ahead. Yeah, you're totally right. The answer was that we opened it in a different mode before. We opened it in writing mode. And if we try and read from it while we're in writing mode, it's not going to work. So we've used another f function that we haven't seen before, freopen, that allows us to take an existing file pointer and just change the mode in which we're using it. So now we're going to open it in reading mode, and that'll allow us to read in our doubles. So this one will give you no surprises with its input and output. We generate an array with a bunch of values, we zero the array, and now we read it back in. However, if I look in my file system, if I look at my files that are around, I've been writing it to this file temp.dat. So let's see what happens if I open temp.dat. Why do I see this? Why do I see junk? Anyone? Why is this not the integers that I thought were there? Lum, what do you think? We too asleep this morning? Okay, too asleep. Someone else. Joseph.
Sure. Is it because it's in machine code and hasn't been translated just yet? It's just been output?
So when you say by machine code, what do you mean?
I mean, as in, it's been, I guess it's been as in instructions directly to the computer.
Oh, it's on the right track, but not quite. Ahmed? It's in binary. Yeah, so remember what we talked about yesterday is that when you store an integer in a computer's memory, we're not storing it as ASCII characters, like a value that would be printed to screen as the letters 4 and 2, if it was the number 42. Instead, it's stored as a sequence of bits, either in typically in 2's complement. Yeah?
So then why don't we just CC those and one instead of these?
Because when we open a text file, we open it expecting to see ASCII, and so our text editor naturally does the conversion and converts whatever the bytes are to the ASCII format. But don't worry, we're not lost. If we want to see the actual numbers that these represent, we can still do it. So there we have OD, which is another utility that allows us to view some of the underlying representations of data. Now, OD still hasn't given us quite what we expected, but it has opened the file, and to the left, it's printed out the addresses of where in the file it's reading. So at address 0, then at address 20, at address 40, but we're still not quite there yet. There's a flag that you can give it, which will octal shorts, decimal, floating point numbers, signed decimal longs, signed decimal ints. I think double precision floating numbers. There we go. Okay. So now for the video. But there's a flag that we can use to get OD to display these as doubles, which is what we actually put in the first place. So let's try this. OD-E temp.dat. Now if we look at what our output was before, fread, we can see 0.679, 1.913, and we can see this is in scientific notation. So it's done by 10 to the negative 1 to account for the fact that this was 0 point. So OD has actually allowed us to view this in its representation as it actually was. Now, you could choose to write data in whatever format you like, and OD is not a magic muffin. It's not going to turn whatever binary data you write, it'll just convert some common formats. Now there are other types of formats that you might want to view binary data in. So another one is in hexadecimal, and XXD can do this for you. So if we do temp.dat, we can see the hex version, which is in base 16, of all the data that we wrote in. And so one of the things you learn as a computer scientist is how to think of data in all these different formats, in binary formats, in ASCII formats, in a struct that you've written directly, in a int, in a long, in a char, etc., etc. And so in our next lecture, either this week or next week, we'll talk a little bit more about some of these formats and how to convert them. So that's all well and good for a bunch of simple demos, but another thing we might want to do is access files out of order. So instead of reading in from the start of the file all the way to the end, we might want to jump around. And this is where we have two additional functions that we're going to use, ftell and frewind, which will tell you where you are and allow you to get back to the start, as well as a more important function, fseek. And this allows you to jump to different points in the file. Now there are 3 different ways you can use fseek. There are a few different ways you can use fseek, but you're always going to have to tell it how many bytes you want to jump along. Or so the key argument here is offset. That tells it how many bytes you want to jump. But the question arises, how many bytes from where? How many bytes from the start? How many bytes from where you are? How many bytes from the end? And so we have these 3 constants that are included in the header file that you can use. So seek set is relative to the beginning of the file, seek car is relative to where in the file your pointer is up to now, and seek end is relative to the end. And so when you're playing around with C, feel free to go ahead and use those. We don't have any demos because they're some of the slightly more advanced stuff. Okay, we are now finally ready for external merge sort. But given that we've already done quite a lot of work on sorting itself, our demo is not going to show you how to actually sort the individual files. We assume that if you know how to merge something and you know how to read it in and you know how to write it in, you're already good. You could write this yourself. So we're not going to provide it. Instead, what we'll provide is a sample bit of code that shows once you have a number of sorted files, so once you've sent them out to the computers, sorted them, and sent them back to a central computer, how do we merge them? So this is mergefiles.c. Let's look at this. So I've got a bunch of files that are in sorted order with some names in them. I have XAA, XAB, XAC, XAD, and XAE. They're not named that way for any particular reason other than the tool I use to generate them name them that. So our different files have a whole lot of different names in sorted order. So this one starts with Arica and ends at Zonya, and XAA starts at Aaron and ends in Zulima. So what we want our merge files to do is to produce one big file or one big output that contains the contents of all the merged files in sorted order. So let's say Aaron is first, and the other ones that are at the top of the files are Abby, Abigail, Abby, and Arica. So out of all of these, which are first? So we saw Aaron in that one and Arica in this one. So they AAR, both of them. That's AARE, AARI. Which of them is first? The first one, AARE. And so what we should expect to still see Aaron as the very first line in our final merged file, and then we would see Arica, which is the next name in the sequence from all of the files, and then we'd have to look at AB, AC, and AD and see which is next. So that's AB, that's ABA, and that's ABB. So the next one would be Abby with an I would be our next one. Now this is a little different from our merge function that we saw before, because this is a multi-way merge. It's not just two things and looking to see which of the two is bigger. We're now trying to compare across all of the files. So let's take a look at our merge files.c. Merge multiple files, all assumed to be sorted. Okay, we've now got our code that's going to look familiar. We've taken a bunch of file names, and we're going to open each of those files and store them in an array of file pointers. Now, remember from last lecture, file pointers are just a kind of struct. They're not a struct that you have to define because they're in our header file, I think in standard io.h. We've also set a maximum number of files that we want to merge, as well as a maximum number of lines that we're going to merge from each of these, just to keep things under control for our own programs when we don't want to demonstrate the use of dynamic memory to solve this problem. Of course, you can get more sophisticated, but for now we're just doing it with a limited number of files and a limited number of lines. Okay, first thing, read the first line of every file. Why are we starting off reading the first line of every file? What information is that going to give us? Michael, why not?
Just to find kind of like which file comes at the very start. So which the first line in each of the files comes at the very start. So as we said before, ARE comes first, and that's in file.
Yeah, so what I needed to do is I was reading in the first name in each of the files because I wanted to find out which of the first names was really first across all the different files. So in order to figure that out, I need to read the first name in each file to figure out which of them should be the first one in the final file. So I've done that. And then I need to find the smallest line out of all of those first lines. So the first line from XAA, the first line from XAB, the first line from XAC, etc., etc. And so I'm going to do a standard little bit of code that you're used to from finding the maximum among a set of items, only I'm using string compare to give me the comparison metric between each of them. Once you've found the maximum, print out the line, and just repeat this process over and over, except making sure to move, when we've read the first line in a file, if it was the biggest one, we now move to the second line in that file, because that first line is already now in our output, so we need to move to the second line in that file. All the other files are still at their first line because we haven't put them in the output yet. So now we look at the second line of the file that had the first one, and the first line of all the others, and we still see, okay, which is the next one that needs to be written out. Repeat this process over and over, and we will get our final merge. When we're done, we're behaving like a good C program, and we are closing all our files. Let's give this one a run. Okay, this is going to take too long, so I'm actually going to use a feature of the shell, which is called globbing. Globbing, G-L-O-B. What this is, it's using the star symbol, and the terminal, or the shell, the program running inside my terminal, is going to take the star and look for all the files in the current directory that start with the prefix, and then The prefix here is x, and then everything that starts with x is going to be fed in as an argument. And I might even be able to force it to show me what they are by pressing tab again. So I can tab complete that into all the files that start with x. Now I don't even need to press tab. I could just leave it like that and run it. Or I could run it this, let me do the star, and press tab, or I could run it that way. They're both equivalent. And now I see it's written the output, but I actually wanted this output in a file. And so I'll call this sorted.txt, and I'm going to use the output redirection operator. Now I see no output on screen because I've redirected standard out to this file. And now if I look in sorted.txt, I see what we expected. Aaron, Erica, Abigail. Oh, turns out I made a mistake before. What was my mistake? I thought that Abby was next. ABBI. What did I miss? So let's go back to XAAA. So what I looked here, I was looking just at the first one and comparing the first line to the first line and all the others. And then I asked what was next. But I asked what was next about all the first lines. What I actually should have done is I said, okay, we've already read that Aaron is the first line overall. Was Aaron the very first one? I think so. Now I'm going to use another utility just to check. This is head. It prints the first n lines. So yeah, Aaron was the first one. And then it was Erica. But I shouldn't just choose between Abby, Abigail, and Abby, because even though those are the first lines in the other files, I've now got to compare them against the second line in the two files in which we've already fed something in. So I should be comparing Abigail and Abby with Abby, Abigail, and Abby. Oh, these names are far too close. The spelling, next time I'll pick some things which have a little more differentiation. And so this shows that our merge actually requires us to, when we've finished reading out the first line in one file, we now move to the next line in that file. Okay, so we've now got our external merge sort well and good. We can sort super large things by breaking them up into chunks, and then we just need to, let's say we have 50 chunks, we'll open 50 files at once, and we only need to look at the first line in each of the 50 files. We don't need to have everything in memory all at once. We can rely on the hard drive to keep the storage longer term. But this takes us all the way back to our discussion earlier about priority queues. That was how we got into this whole discussion of merge sort versus heap sort and the different data structures that we could use. So we get kind of an interesting question here of could we actually use a priority queue to make our large sorts faster? And there's some really recent research on the topic actually. The naive thing to do, which obviously isn't going to work, is to put everything in a massive priority queue and pull things out one by one. Why isn't this going to work? What's the problem with a massive priority queue? Bronson? Yeah, it takes up too much RAM. It's the same problem. We can't, if we couldn't fit the things without a priority queue, we certainly can't fit them in with a priority queue. So this takes us to external priority queues. And it turns out that there is a very close correspondence between external sorting and priority queues. So there's this beautiful paper that shows that there is an equivalence in general between priority queues and sorting. Just like we saw that heap sort was, we developed a priority queue to make, and just as we performed heap sort by using a priority queue, because a heap is essentially our way of implementing a priority queue, and then we got an n log n sort, this tie runs really quite deep. There's a theoretical result proving that the two are always equivalent. But doing it naively this way wouldn't fit in the memory. And so we can do external merge sort with a priority queue where we split the data into chunks, we sort each chunks, and then we do our merge using a priority queue. So rather than our technique that we saw in mergefiles.c where we compared each of the lines, we could put each of the lines into a priority queue and then pull them out one by one. And using a data structure would actually improve the way that we do this external merge sort and can give us a bit of a faster runtime. But we have this other equivalence result that shows that there that is the same thing to do it this way, to use a priority queue, as to just sort them, say to sort all the first lines and then pull them out and merge them. So we have this very close tie between all the things we've been doing. And if you actually go down and try and start to do the mathematics behind it, you can prove very close equivalence between all of them in really deep ways. So how long does our sorts actually take? How long does our merges take? It takes k n log n time and O of k n space for k splits, each of size n. And you can prove this to yourself if you want in your free time. You've now got all the tools that you need to do it. So Wikipedia also does have a little bit of wisdom for us about this general topic. It's a little hard to read here, but it says that theoretical computer scientists have detailed other sorting algorithms that provide better than O of n log n time complexity. So we've finally finished with all our sorting, but we didn't find anything better than O of n log n. So what does it say here? Assuming additional constraints. Okay, so there's Thorpe's algorithm, which only works if you assume that your keys have a finite size. So let's say that we know that all our numbers are under 50, then we can write a better algorithm. There's a randomized integer sorting algorithm where we know that our keys are all integers that takes O of n root log n expected time. So we can do better if we know it's just integers. And then there's also an algorithm for real numbers. So while we've taught you great general purpose sorting algorithms that work for any kind of data, if you know some more things about your data, and this is a theme with all our algorithms, you can often do better than the naive version of your algorithms. Okay, whew, that was a lot. We've finally finished sorting. It took us only 9 weeks. But we've still got some other problems for Ticketmaster. Now, if you remember, who here remembers reading about the Taylor Swift Ticketmaster debacle? I can see a couple of hands at least. Yeah, so Ticketmaster's got all kinds of problems, and we've only solved one of them. Violet comes to the desk, and she can't remember her seat number. She's got a QR code thing, her ticket scanned in, she's bought it, all the priority stuff worked out, but now we need some way to look up a matching between Violet and her seat number. Now, we've already seen an abstract data structure that could do this. Who remembers what it was? Yeah, Oscar? Dictionary. Yeah, it was our dictionary type. But our dictionary type had some problems. It was actually going to take O of n time or O of log n time to do a bunch of operations. We had this beautiful slide a couple lectures ago that showed that we could implement it a whole bunch of ways. But it wasn't good enough if we had to do thousands and thousands and thousands of lookups and we were Ticketmaster. So this takes us to our question before of how can we find and store and find people's seats? So given a ticket number or given a person's name, how can we find out where in the stadium they're meant to be? So here's our picture about the dictionary that said we had all these different ways of implementing it. If we used a binary search tree, we could get O of log n average case time, but we're all algorithmeticians now. This takes us to probably the most exciting but also most complicated data structure we've learned this semester. Not from the perspective of how long it'll take you to understand, but if you actually dig down to more of the details, they're really complicated. So complicated that this is the first year I'm teaching about these. I spent hours and hours and hours digging into the literature about these because they were suddenly so interesting in all of their different behaviors. To the extent that I consulted with a bunch of more expert theoreticians and algorithmeticians to see if I could learn more about hash tables. And this is our data structure, the hash table. Now, it might look pretty simple. It looks just like a dictionary at this point. It's a mapping. But the way that we make the mapping work is going to be important. So this is our goal. We want to have some kind of table that matches our different people to their seat number. It was invented in 1953, more or less, by a few researchers at IBM. But while I've listed all their names here together, it was actually two groups of people in different parts of IBM that came across the same idea at almost the same time. So in January 1953, there was an internal memo about like, hey guys, I think I found a way to do this. And at the same time, another group of researchers were also like, hey guys, this seems like a really cool data structure. It also led to one of the first formal analyses of algorithms by Don Knuth in, I think was it 1953 as well? I don't remember. I'll get the year for you later. The basic idea of a hash table is to convert a key into an array index. So even if our key is someone's name, we want some way to convert it to an index in an array that works really, really quickly. And how long if we know the index in an array, how long does it take up to look up that index? Of 1, yeah. So if we can convert the name into an index in O of 1, then we can do the lookup in O of 1, and then we can do a search in O of 1. Now we also would like to be able to do this for an insertion. How long does an insertion take on an array if you know the index? Min, one of you? One of the Mins, do you want to answer? I don't know your last names, so it makes it tricky. How long does it take to insert something into an array if I know the index? Nope. Victor? O of 1, it takes one step. You know the index, you go direct to that index, you put the thing in there. So again, if we have a way to convert our key, say our string into a fixed length string, into a number in roughly O of 1, then we can do our insert in O of 1. And we're going to label these, instead of ID and seat number, the more common terminology is going to be key and value. And our key is going to be the key into our array, that number that tells us at what index we should have to be. So the way we do this is by using something called a hash function. Now a hash function has a lot of properties. You can go into a lot of depth studying these things, but the basic version of it maps a large input space, so say all possible English strings of less than 256 characters into a small output space. In this case, I've said output space of a table, but hash functions generally just the output space is smaller. So it might take all names of all English strings of 256 characters and maps them to an array index of between 0 and 1,000. Might be one example. And we won't talk too much about how you design one of these functions other than to assume that they exist. So let's introduce just a small bit of notation. Let's say we have a key A that we're going to want to figure out how to convert into a small number into an array index. We'll have some function h, that'll be our hash function, and h of A will be equal to t, and t will be less than n, where n is the total number of items that we want to insert into our array. And then we're going to store the value corresponding to A at index t. So who can give me an example pair of like an A and of a key and a value, just to help refresh our memory? Miguel? Just a key and a value for our Taylor Swift concert. 3 and 75, so seat number 75. And is the 3 the key? Yeah, Michael. And we're going to convert Michael into 3 and then 3 into 75. So we've got this multi-stage process. This structure is called a hash table, or in some instances you might also hear it referred to as a hash map, because that's what Java refers to it as. Yeah? In some ways, yes. That's actually a really nice link. So even though our assignments are kind of independent, we've also been trying to introduce new data structures to you kind of on the sly through them. So we will explicitly talk about either tomorrow or next week the hidden data structure in assignment 2 as well. But the hidden data structure in assignment 1 was a little similar to a hash table in some ways. Not identical, but bore some similarities. So what makes a hash function a good hash function? There is a lot of theoretical discussion about this, but at a very high hand-wavy level, our goal is for the chance of an item ending up in a particular place in the array should not be particularly dependent on what the key is. So you shouldn't be able to tell just because someone's name starts with A that it'll be earlier in the array, or just because their name starts with B, it should be later in the array. And likewise, each of the places in the array should be more or less equally likely. Now, there are all these complicated ways of defining it. What do we mean by equally likely? Equally likely dependent on what? Don't worry about that for the time being. Just keep this general idea in mind. But there's a trap. What if location T is already occupied? Now, if our hash function is really mapping a large input space to a small output space, we've got something called the pigeonhole principle. Put your hand up if you've heard of the pigeonhole principle before. Pigeonhole principle basically says if you have 100 pigeons and only 50 boxes in which to put pigeons, then you're necessarily going to be doubling up some pigeons in some boxes. So we've got this problem. We have a large input space and a small output space, and so we're going to get some collisions. And the topic of collisions is going to occupy both the rest of today and the first chunk of tomorrow. So there are a few different ways that we could imagine handling collisions. The first way is we could just do a better job at hashing. So we could come up with an amazing hash function, make sure that we're using fewer items than there are slots, and make sure that our hash function is so good that for all these particular items that we're going to be handling, all of them end up in their own slot. Now, this is a very lofty goal. We're probably not going to be able to get all the way there. But we could also expand on this a little and say maybe have a second hash function that's independent of the first. And if we end up with a collision when we use our first hash function, then we try the second hash function and put the item in the second place. And turns out if we do this enough, if we use enough independent hash functions, we can do okay some of the time. So that's strategy 1. Strategy 2 is we can allow items to leak beyond the place that they're meant to be. So let's say your Michael's ticket was meant to be in index 3. Perhaps we push it along to the next index, to index 4, if we get a collision at index 3. That's going to have some complexities too, as we'll see. And then our last technique is closed addressing, where if you get a collision, just store multiple things at the same place. And we'll talk about how we do that tomorrow. So I think we've probably been going fast enough, so I'm not going to go into any of these techniques today. But come back tomorrow and we'll discuss all of these a little more along with their runtime analysis. And maybe, just maybe, we'll get to the last data structure of the semester. Thanks very much, and I will see you all tomorrow. See you all next week. Wait, see you all tomorrow. Yes, I will see you all tomorrow. Have a lovely afternoon.